So now let us dive into these concepts more. So let's understand how one host machine communicates with another host machine if they are in same network, and similarly how one host machine communicates with the other host machine if they are in a different networks. So to understand that, let us look into the following concepts one by one. So for the first one is resolving logical addresses to hardware addresses. Say a host cannot directly send data to another host's logical address. A destination logical address must be mapped to a hardware address so that the data link layer can package a frame to transmit on the physical medium. So the Address Resolution Protocol, ARP, capital A, capital R, capital P. The Address Resolution Protocol provides this mechanism for Internet Protocol version 4 on Ethernet networks. So ARP, Address Resolution Protocol, allows a host to determine the MAC address for a particular destination IP address. So let's consider the, uh, the diagram which is shown on the screen. So this demonstrates the steps required for host A to communicate with host B if they are in same network. First, let's begin with host A. So host A is our machine which is on the left side, and host A will determine if the destination IP address of 10.1.1.6 is itself. So if that address is configured on a local interface, so the packet never leaves host A. So in this example, 10.1.1.6 is not locally configured on host A. So next, host A will determine if the 10.1.1.6 address is on the same network or subnet as itself. So host A consults its local routing table to make the determination, to make this confirmation and determination. In this example, the subnet mask is 16. You can see the subnet mask, that CIDR, is / 16. Thus host A's IP address of 10.1.1.5 and the destination address of 10.1.1.6 are on the same network, that is 10.10.1. So that is the common network both are in. So this is host A and this one is host B, and both are in the same network because mm, based on our subnet mask or CIDR. Okay, so now because host A and host B are on the same network, host A will then be broadcast an ARP request, as you can see on the screen. So asking for the MAC address of the 10.1.6, 10.1.1.6 address. So MAC address, as we have known before, media access control, or it's a physical address of each machine. So now host B ARP request is sent to host B, and host B responds to the ARP request. So ARP request has been sent to the host B, and then now host B responds to the ARP request with an ARP reply containing its MAC address. MAC address could be anything A, B, B, so that we have seen that's a physical address. Then it will send the uh, host B send the MAC address back to the switch. So host A can now construct a layer 2 frame with a destination of host B's MAC address. So host A host A forwards this frame to the switch, which then forwards the frame to the host B. So um, this is how uh, two host machines which are inside the same network initially communicates and make the confirmation and determination, then to pass over the data to each other. So then we have one more example to look up, that is, now let's consider a slightly modified scenario between host A and host B. Again, host A is on leftmost side and host B is on rightmost side. So here again, similar way as the before the previous example, host A will determine if the 10.1 10.2.1.5 is itself, in this example 10.2.1.5 is not locally configured on host A. So now, so here the network itself is different, so that's the reason host A's IP is 10.1.1.5, whereas host B is 10.2.1.5. Okay, so next, host A, this is our host A, and host A will determine if the 10.2.1.5, that is host B's IP. So host B's IP address is 10.2.1.5, whereas host A is 10.1.1.5. So host A will determine if the 10.2.1.5 address on the same network or subnet as itself. In this example, the subnet mask is as usual. The CIDR is /16. Thus host A's IP address of 10.1.1.5 and the destination address of 10.2.1.5 are not on the same network. So because host A and host B are not on the same network, so host A will parse its local routing table for a route to the destination network of 10.2.x.x./16. So hosts are commonly configured with a default gateway to reach all the destination networks. So now host A has to determines host A determines that 10.1.1.1 address on router A is its default gateway. So now host A has, because a router is the one basically default gateway we have discussed in our previous slides also. Now the default gateway was decided for the host A is 10.1.1.1 on router A. So now host A will then broadcast an ARP request asking for the MAC address of 10.1.1.1 address. So now the host A has sent it to the switch, and through switch it has gone to the router A and requesting for the MAC address of gateway. It's just asking the gateway only. So remaining thing will be done through the gateway because these are in different networks. So this is one network that is 10.2.1. This is in another network that is 10.2, whereas the intermediate piece is our router which is at the center. So this is the gateway for the both the networks. So for this host A, the gateway is 10.1.1.1. So here it is, you can see that this is our gateway. So now host A has sent a ARP request. Now let's see what's going to happen. So now router A responds to the ARP request with an ARP reply containing its MAC address. So basically router A will respond back to the MAC address with the response back to the host A with the MAC address of router A. So that's it. The host A got the response from the router A. So and then host A can now construct a layer 2 frame with the destination of router A's MAC address. Then a response to the ARP request with an ARP reply containing its MAC address. So router A can now basically create a layer 2 frame destination with a layer 2 frame with a destination of host B's MAC address also, because we have a router A at the center, so it can it can connect with the host B through the router A. So if you see that um, animation on the screen, so once the connection is established from host A to router A, then the next task of the router A is to uh, establish a connection with the host B. So now router A has requested for the MAC address of host B, and then host B has responded with the MAC address back to the router, and then once it's sent to the router, now it's all done. Now host A and host B are connected through a router. So note that as a packet is routed, the source and destination IP address remain unchanged. However, both the source and destination MAC address did change. So this is because a MAC address contains no network hierarchy and thus is the only significant on the local network. In this scenario, host A and host B could not communicate directly using layer 2 addressing. At every routed every routed hop, the source and destination MAC address are registered to reflect the source and destination hosts on the local network. So the source and destination IP address will only be changed if NAT is used. So now let's look uh, look into ARP uh, uh, and understand few more points from ARP. So ARP table, basically here we are talking about ARP table is nothing but address resolution protocol table. Address resolution protocol table. So a host can build an ARP table that contains a list of IP to MAC address translation. So the ARP table is only locally significant to that host. So there are two methods to populate on ARP table. One is statically and second one is dynamically. So either you can have statically ARP table and then dynamically populate ARP table. Either you can statically populate the ARP table or dynamically populate the ARP table. A static ARP entry is created manually on a host and will remain permanently until purposefully removed. More commonly, ARP tables are built dynamically by caching ARP replies. Entries will Cached entries will eventually be aged out of the ARP table. So the aging time will vary depending on the operating system and can range from several seconds to several hours. So now let's look into troubleshooting troubleshooting IP using ICMP. So the Internet Control Message Protocol ICMP we have seen in TCP IP protocol. So the Internet Control Message Protocol is used for a multitude of informational and error messaging purposes. So the following is a list of common ICMP types and codes. So the first one is a dash and just an hyphen for destination unreachable, and 0 network reachable, 1 host unreachable, 2 protocol unreachable, 3 port unreachable, 4 fragmentation needed, and don't fragment flag set. 6 destination network unknown. 7 destination host unknown. 9 destination network administratively prohibited, and 10 destination host administratively prohibited. Sorry. So the two most common troubleshooting tools that utilize ICMP are packet internet grouper. Normally we call it as a ping. So ping is a core connectivity troubleshooting tool which utilizes the echo request and echo reply ICMP messages to determine if an IP address is reachable and responding. So ping will additionally provide the round trip time between the source and the destination, so usually measured in milliseconds. And trace route determines the routing path a packet takes to reach its destination. So trace routes will not only identify each router the packet has been forwarded through, but also measure the delay experienced at each router hop. So let's look into this practically. So here we have a VPC, and then okay, it got timeout. Okay, let me log into it. Let me give MFA code, multi-factor authentication code. Yes, it is 4444. Yeah, we are on. So let me get back to the VPC so that I can show some of the things. See, this what I just want to show this route tables. So here you can see the route table. So and then internet gateway. Here you can see the internet gateway, and we also discussed about the elastic IPs. So this is our elastic IP, and we also discussed about the NAT gateway. Here is the NAT gateway. So these are the best examples of NAT gateway. And if you are still confused about that CARD type type of IP. So this is how you can create a CADR type of IP. So and I just want to show some examples of that. So here also I'll put CADR. Yeah, uh, if you look into this, yeah, here I have IP based routing. So when I click on when I want to create a CADR collection type, if you see, here is the CADR blocks. This is the IP, and then after that, this is version 4, you have 24. So /24. This is our CADR. So what does it mean? So 24 means, so obviously it says total 24. So 8 plus 8 plus 8. So 16 plus 8, 24. So the first three octets determine or define network, and only one octet determine host. So what does it says? It's a basically class C default subnet mask. So this is an example, and similarly we can have a lot of other examples. Everywhere you will find this kind of examples. If you click on elastic IPs, you can allocate elastic IP to that virtual machine, specifically to that virtual machine. Here see I'm in this instance, so I can click on elastic IP and allocate elastic IP for this. See, automatically gets taken network broad grouper, and then I can attach elastic IP, and this is, yeah, we select Asia Pacific, and my one instance is running there, and this is our VPC. And you see here, come down. So this is my VPC. If you see the address type and CIDR of this VPC, so the Mumbai VPC 172.31.0.0./16. So just explain me what does this mean. So it's here, or else you can see here also. So what does it mean? So it's internet protocol version 4, and then it's 16, so 8 plus 8. So first two octets define network, and then remaining two octets define host. So basically this is class B type subnet mask. So you can have close to 64,000 16,000 networks, and approximately 64,000 host machines per network.